Hey, let's begin with the comparison test. So, we already learned about lot of tests, and in this chapter of infinite series, we have come across among P series test and lot of other tests, geometric series and up so on. And now we will discuss about comparison test, and we will discuss about some of the examples in this lecture, and we will just uh, use our previous knowledge and also this comparison test knowledge in order to look at the few more examples. And in this comparison test, we're going to learn about to compute from one series which we have already observed and to predict the another series by looking at its some properties, and we're going to compute whether we get by just looking at its properties of previous series to the new one series for which we are predicting our divergence or convergence. By that properties, we're going to look at whether new series is convergent or is a divergent series. So this is all whole idea about the comparison test, and we're going to just mix up our whole knowledge and use in order to solve some examples. We're going to use concept of comparison test and lot of other tests which we have discussed so far. So let's begin with the content of the chapter.
Let's begin with the comparison test. So let un and vn is series. Summation of un and vn be a positive term series, and if un by vn as n approaches to infinite, we get un upon vn equals to L, which is finite and non-zero. If we get any finite term and non-zero, then un and vn both converges or diverges. So, and if we get 0, so 0 is a finite, and if we get un upon vn equals to 0, then we will get vn converges, then un also converges. So we have to check the convergence of vn to locate the convergence or divergence of the series un. To locate the series un, to look at its properties. Now let's look at the third one. As n approaches to infinite, un upon vn equals to infinite. So it means if vn diverges, then un also diverges. So these are the three properties we have to use to solve comparison test problems. So let's begin with the example number 1. So examining the convergence of the series. 3 upon 5 plus, first part is 3 upon 5 plus 4 upon 5 square to so on. Now if we separate these terms into if we separate this term 3 upon 5 and 3 upon 5, if we take 3 upon 5 up to 3 upon 5 cube up to so on in one side, and 4 upon 5 square plus 4 upon 5 4, and next step we're going to take it as a common, and now we're going to take common ratio of both these. Like in the first case we get 3 as a common. In this example, let's solve this example. So we get 3 common, then we will get 1 upon 5 plus 1 upon 5 cube up to so on. So we will notice that then in the next step we will reach at 1 upon 5 raised to power 5. So we will notice that both these terms in this also case we will get started with here it is 3. Okay. So here it is 3, and we will get that we have common ratio with 1 upon 5 square in both these terms. So then if both these terms have a common ratio, and we're going to find whether it's convergence or it's a divergent series. Now this is not the part of the property we have discussed, but this is simple property of which is numerically less than 1. So we know that if common ratio is less than, using the property of geometric series, if it is less than 1, then we must get sum up to series as a finite series. So thus un is convergent series. So un is this, okay. So un is also convergent. Here also vn is also convergent. So overall we will get that we get the vn also has a common ratio 1 upon 5 square, which is numerically less than 1. So if common ratio is less than 1, then we will find that our series is geometric series, as this geometric series 1 upon 5 square plus 1 upon 4 is to power 5 is to power 4. We take 4 as a common in this Vn series, and then we're supposed to get our Vn series as a, because when it reaches to infinite term, we will get that point 0. So if we add at 1 upon 5 square plus 1 upon 5 is to power 4, we will get always convergent series, because we will get our next term be less. Common ratio is always less. So common ratio is defined as whether we get convergent or divergent. So this is already you are familiar about the P series test and geometric series test. Now let's look at the. So now we will get that Vn is also convergent. So thus our first answer is Un plus Vn is also convergent, because we get adding, we will get our initial quotient. So now let's look at the second one. So the second example we have, now this is going to be good example. Let's see. So we have 1 upon 1 plus 1 upon 2 is to power 4 upon 3 plus 1 upon 4 is to power 3 up to so on. We will get that this is nothing but P series test. So you might be confusing it with a geometric series, but it's not a geometric series. So its n is actually n is actually constant, n is actually variable. We will get the value of n1 in the series of 1 upon n equals to 1 up to so on up to infinite. Here P is constant. When P is constant, so then we will get that it's a P series test. You are already familiar about P series test. So now we know that if using property of P series test, when we compute this, we will get that 1 upon n is to power p, which is greater than series, so it must also be a convergent series. So using the P series test, the given series is convergent series. Okay, so first of all we will get at 1 upon 2, here we have to convert into P series test. 1 upon n is to power 4 by 3. So we will not always given us in that form. So we will just make 4 into 2 raised to power 2 and go into exponent 4 by 3, here also 4 by 3 up to so on, and we will finally get 1 upon 2 4 by 3 up to so on. Then we will get our P series. So now let's look at the second question. Now test the convergence of the series. 1 upon 1 to 1 into 2 into 3, this is in denominator, whole things in the denominator. So now let's solve this question. Here how we write it. So we can write like in this example, we can write n into n plus 1 into n plus 1. Let's suppose now un is 2n minus 1. Why this is 2n minus 1? Why not n? Because if you put 1, because we're going to just split it into these two series into these forms. Okay, so let's see. Let's look at. Now un is 2n minus 1 upon n into n plus 1 up to so on into n plus 2, and this is supposed to be say. So if we take 2n common from here, we will get 2 into n into 2 minus 1 upon n, and here we get n cube common, and we will get 1. N is always outside, and we will get n. Here we get from here we will get n outside, and we will get 1 upon n, 1 plus n. So the 1 plus 1 upon n. Here also we will get n as a common, 1 upon 2 upon n. So now this is our denominator also. So we will cut this n into with this in denominator with n cube, and we will get left with n square. So now we're going to, actually this is supposed to be 1 3 and this is 5. So that's how we will make it. So that's how we will create un, which is 2n minus 1 upon this, already written here. So if that's the case, then we will get, otherwise it will be only n. Okay, so there's some mistake here. So now let's move further. So hope you get it. So in the numerator we will get 2 minus 1 upon n. Now we will do our further step. So let's compare un and vn with 1 upon n square. So vn is equals to 1 upon n square. Now we have to compare un and vn. Here we have vn is equals to 1 upon n square. Okay, so here how we assume 1 upon n square equals to v. So if and un is except 1 upon n square, everything is un. Okay, this is supposed to be un, like 2 into 1 minus, except n square, everything is un. 2 into 1 minus 2 minus 1 upon n upon 1 upon 1 plus n into 1 upon 2 plus 2 by n. Now we will get un upon vn. So un upon vn. Now if we divide this whole term, this is supposed to be un. This whole is supposed to be un, and we assume by any intuition we will get that vn is, let's suppose vn equals to 1 upon n square. Now if vn equals to 1 upon n square, when we divide both these terms, n square will cancel out. So we will left with this term only. Now if we put n raised to power infinite, we know that using this, so this is a finite and non-zero. So because we will get, as n approaches infinite, 2 minus 0 equals to 2, and in the denominator we will get 1 plus 0 into 1 plus 0. So that's supposed to be 1 into 1, and we get 2. So this is finite and non-zero. And now we will notice that un and vn converges or diverges together. So if that's the case, if it's a finite and non-zero, then both should be converges or diverges together. Now we have vn equals to 1 upon n square. Now using the property of p series test, and if p is greater than 1, we will get vn is convergent. So that's how, using this property, using the test number 1, first property of test number 1 is finite and infinite. If un by vn n approaches infinite is, we get finite and non-zero answer of un upon vn, then we will get that both should either converge or diverges. So now if we have vn equals to this, we have let this vn equals to by our intuition, because using by examining this un, we will assume vn that if we divide it, what we will get. So that's how we assume it. So now let's move further and let's see. So it's a convergence. So as we have discussed about the p series test, so it says vn is convergent and un is also convergent. So that's how. Let's move further. So now let's look at the third question. So test the convergence of the following series. So un is 1 upon under root n plus 1 upon under root n plus 1 up to so on. Now if we take under root n common from denominator, we will left with 1 upon under root n into 1 upon 1 plus this is supposed to be full. Okay, so if we, in the denominator part, if we get under root n common, then we will get then we must get 1 upon n up to 1 plus 1 upon n. This is supposed to be done. Okay, this is what is written here. Okay, so let's move further. So let's compare un and vn. So let's now here in the previous question, we assume vn equals to 1 upon n square. In this example, we assume vn equals to 1 upon under root n. So in order to, when we divide un by vn, we will cut this and 1 upon under root n. So that's how we move further. So let's see. So let's see now. When we divide it by, we will get 1 upon under root cancel out. Then we will left with 1 upon 1 plus 1 upon 1 under root of 1 plus 1 by n. So if we put n equals to infinite, this will give us 0. And 1 upon 1 plus under root 1. So 1 upon 1 plus 1. So 1 by 2. We will get our answer as 1 by 2. Now let's move further, which is a finite and non-zero. It's a finite or non-zero. This is supposed to indicate un is either convergent or diverge together, un and vn. And we have since we have vn equals to 1 upon n under root n, so p is less than 1, so this is supposed to be divergent as always. So vn is also divergent using the property of comparison test. So that's how we compare by first let any vn by our own intuition, we will let vn and we test on it if it's a convergent or divergent. Then in order to find the relationship between, compare vn and un is what we have taken, un is what we have given, okay, and vn we assume, and using the property of vn we will find that from any part of the question, if it's a divergent or convergent, and un upon vn by examining, we will get if it's a finite or non-zero. If it's a 0, then we will get something other. We will get that vn is convergent or anything else. So if vn is convergent, then un is also convergent. So that's all. So that's how these properties helps us in understanding the comparison test.
I hope you enjoy my content, and please don't forget to like, subscribe to my channel. Till then, keep learning and keep exploring. And as always, feel to email me at dsvfx6789@gmail.com.